Okay, so now we can talk about root mean square values. All right, now we've got a definition there, and it says the root mean square of an AC current is the DC potential difference or current which dissipates the same amount of energy as AC. Now, dissipates is like a big word, but it basically just means that in a resistor, like a light bulb, right, it's going to use the same amount of energy as that AC. Okay, right, so why do we care? What do we do this with? Let's have a closer look. So here we've got a representation of a typical AC current. We've got that sinusoidal curve, and what's the difficulty with this is if we, for example, want to do a power calculation, right? The power is equal to the V squared over R. That's a formula that we can usually use, right? So if we want to do a power calculation, well, what on earth do we use for V? Because from one moment to the next, the V actually changes, right? So the V changes from one moment to the next. So what are we going to substitute in? Well, the solution is that we say, okay, let's pretend we have a DC source like the type that you get from a battery, right? So not like from a DC generator where it's hopping, but from a battery where it's a constant current, right? So we ask ourselves, what constant current, consistent current do we need like this so that when we hook a light bulb or something up to this and to this, the light bulb is going to burn equally as brightly. So in other words, what DC current is going to give us the same amount of energy, right? And it makes sense that it's going to be somewhere between that highest point and the zero, right? And it turns out that we can calculate it, and it's called the root mean square value, right? So we've got a formula here. We were talking specifically about voltage here, but it could be the voltage or the current, right? So let's say, for example, this max value here is 260 volts, just as an example, right? So what that would mean is that the VRMS is going to be the Vmax, that is the 260 over the square root of 2, right? So 260 over the square root of 2 gives us an answer of 183.85. Okay, cool. So what that means is our direct current that we need in order to use the same energy to get the light bulb to burn equally as brightly has to be at the 183.85 volts, right? Now, why is this useful? Well, it's useful because the DC current is consistent, right? It doesn't change from one moment to the next, which means we can go and substitute that amount in order to actually go and do a power calculation. In other words, in order to go calculate how much energy something uses per unit time, right? And so you will see that the power that something uses, we're calling it the average power because yes, there is a little bit of a change from one moment to the next. But yeah, average power, right? We see that we can actually use the root mean square values in order to go and calculate it. Okay, so root mean square values are useful because they allow us to calculate the power or energy usage of something that is connected to an AC source. Okay, so we've seen these formulae here. So basically, in order to find the root mean square, all you need is the max, and then you can go and substitute that into the formula. Okay, so let's do an example. So for this example, the following graph represents the voltage output of a 200 watt average power supply, and it asks what is the root mean square value of the current produced by this power source. Okay, so we can list what we have. The average power is 200 watts. Okay. And we know the Vmax, right? So I hope that this is on a nice big screen so you can see that 310. We know the Vmax, right? So the Vmax is going to be the 310. right? And we need to find the root mean square value of the current that is being produced. So we want IRMS. Okay, right, so the average power, we know we can do calculations involving only the root mean square values, right? So it makes sense that we probably want to start with our V max and turn that into a root mean square value. Okay, so RMS is going to be equal to the max over root 2, and that's going to be 310 over root 2, and then we defer to our calculators, and my calculator says 219,20. Okay, so that's then 219,20 volts. Okay, great. So then we're trying to find IRMS, and we have P average, and we also now have VRMS. So if you consult your formula sheet, you might find that this P average is equal to VRMS. IRMS is the appropriate formula to use. So here we can say 200 is equal to the 219,20 times the IRMS. Okay, and so we would go 200 divided by that answer from the previous one, and I get here that the IRMS is going to be equal to 0.91 ampere. Okay, so that is an example of how we would use these root mean square numbers. So now what I would like you to do is please pause the video, try these two examples, and see if you can figure it out. Okay, fantastic. Well done. If you gave that a try, let's see whether you were on the right track. So it says that a blender is plugged into an ordinary wall socket, right? Now, ordinary wall socket, that means AC current, right? Because that's what we get at home from Eskom. The appliance is rated at 1000 watts. So that's going to be the average power usage. And then it tells us that the root mean square potential difference delivered is 220 volts. So that's going to be VRMS, right, which is the 220. So then it asks, what is the root mean square current that flows through the device? Now here we're in luck. It's actually quite a simple calculation because the P average we have the VRMS, and we're trying to find the IRMS. Okay, and so when we substitute in there, we get the 1000 is equal to the 220 times the IRMS, and I hope that you're going to lay out your workings more neatly than me. So 1000 divided by 220 gives us 4,55. Okay, so our IRMS for question A is going to be 4,55 ampere. Well done if you got that. Right, so then for the next one here, we've got an AC generator and it's producing 1500 watts of power. Now, the only items that are using the power that is produced are a light bulb and the wires that carry the current to the light bulb. Okay, so this is quite interesting because usually we are told to ignore the resistance of wires, which means that basically energy or current moves through them for free without an energy penalty. No energy is used to move the current through the wires, and that's a bit of a simplifying assumption. All right, so here we do actually lose some energy by moving the current through the light bulb, through the wires. Okay. So the light bulb has a resistance of 10 ohms and a root mean square voltage of 120 volts is delivered to it, right? How much power is used to carry charge through the wires? Okay, so the power, the 1500 watts, well, basically it must be being used in two ways, right? Some of it is being used to light up the light bulb, and some of the power is being used to transfer current through the wires, right? So here, what we can do is find the power that the light bulb uses first, right? So there, to find the power that the light bulb uses, we've got the VRMS and we've got the resistance. So we can use this V squared RMS divided by the resistance, and the power from the light bulb will then be 120 squared over 10. And let's see what we get for that. 120 squared over 10 gives us 1,440. Okay, so this means that the light bulb is using 1,440 watts of that power, which means that the wires, I'm just going to say P wires, must be the 1,500 that's being supplied minus the 1,440 that the light bulb is using, and that's going to be 60 watts. So what does that mean? Well, since power is equal to the rate at which work is done, right, 60 watts then means that we are losing 60 joules of energy for every second that this generator is operating. So 60 joules of energy is being used basically to heat up the wires, because that's where the energy goes when we lose it, when we transport things through wires. Okay.